Alright, let's go ahead and get started with lesson 1, standing waves. To begin this lesson out, I want to show you a short video that I hope will help you to understand standing waves a little bit better and give you some examples. So let's go ahead and get started with that video.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 115. It's on standing waves. Standing waves are like they sound. They're waves that appear to stand still. And so an example of a sound standing wave is the waves found inside a vuvuzela. And so you blow on it, you get that sound. You blow it with a higher frequency, and then you can even try to pierce your lips a little bit more and get an even higher frequency. But what's happening is you have these specific standing waves that sit within the chamber of the vuvuzela. Now, a wine glass works the same way. If you rub your finger with a little bit of water around the surface of it, what you can do is generate these standing waves inside the wine glass. What you're doing is vibrating the sides, and as you do that, you're vibrating the air, and since you have a standing wave inside there, it makes this pitch. Add water to it, and you're going to have a slightly different pitch. And so waves can either be traveling or standing waves. Traveling waves will move from one place to another, and standing waves will appear to stand still. Now, when you look at it, it's kind of an illusion. They're standing still, but the traveling waves are bouncing back and forth. In other words, they're being reflected off the boundaries, and then there's interference to create these standing waves. And so if we look at this animation, the dark wave is going to be the standing wave, but in the background you can see the blue and the red waves that are bouncing back and forth, and it's the summation of them that creates the standing wave. Now, if you notice, that standing wave is going to have areas where it's not moving at all, and that's due to destructive interference, where the waves are canceling each other out, and we call those in physics nodes, areas where it's not moving. And then we're going to have total constructive interference in certain areas, and we call those antinodes. That's where it's moving the maximum amount back and forth and back and forth. And so an example of this could be found in instruments, for example. So a string instrument is going to be fixed at either end, and this animation is a good example of that. It's fixed on either end, and as the waves bounce back and forth, you create these standing waves. If we shorten that, like on a guitar, then we can get different pitches. A tube is going to be the same way. A tube could be open on both ends like a flute, or it could be closed on one end like a vuvuzela, and that's going to create these standing waves as well. So let's start with traveling versus standing waves. And so this PHET simulation, I'm generating some waves. Those waves, and this is just kind of theoretical, are moving out the door, and then they've moved on forever. But if we add a boundary on the other side, in other words, if we add a fixed boundary, you can see now there's a reflection back. So those waves didn't just keep going, now bounce back, and now they're going to bounce back again. And as that wave goes back and forth, you can see that we're starting to generate these standing waves. And you can even see those nodes and those antinodes. In other words, those areas where it's not moving and those areas where it's moving quite a bit. So this is an animation of standing waves, and so what we're doing is as the blue wave moves to the right, becomes the red wave, which moves back to the left, and it just keeps going and going and going. We're getting destructive interference, that's causing these nodes where they cancel each other out, and then we have constructive interference, and that's creating these antinodes, where those two waves add together to make a much bigger wave. Now, an example of this, if you've ever played baseball before, when you hit the ball, sometimes you'll hit it and the bat will kind of buzz in your hands. In other words, it vibrates quite a bit. And the reason why is that you're hitting the ball on an antinode, an area where the waves going up and down the bat are actually constructively interfering to create a huge vibration there. And we refer to it as the sweet spot, the spot on a bat where the node is, where you don't have much vibration, that you hit the ball and you don't feel really any vibration at all. And so let's go.
Alright, so I hope that video gives you a brief introduction to standing waves. So we have a diagram in your notes here that depicts a standing wave. And so we can generate a standing wave by taking a rope and fixing one of the ends of the rope to a wall, as indicated in this diagram here. The other end of the rope is going to be a fixed end with someone holding that rope. And then the wave is generated by the hand moving in an up and down motion. This creates the vibration, which then allows the wave to move along the rope to the wall. But instead of that wave continuing to go, it's actually going to essentially reflect off the wall and then go back again. And so you're going to get this wave that continues to go back and forth, generating that standing wave, which was shown in the video. If you add more energy, more vibration, then you get what you get is a node region, which was said in the video is a region in which the reflecting waves going back and forth create an area where there is no movement at all in the wave. And so you get these antinodes where that's where the maximum movement of the wave is shown, as you can see by the maximum height and the low point here. That's where most of the movement is generated in the wave. And then the node, there's absolutely no movement whatsoever. And we can see this with the guitar, where you have two fixed points on the guitar string. And when you pluck the guitar string, it creates a standing wave that generates movement back and forth. And it will even create these node regions where there's no movement in the wave. Therefore, there's no sound that's generated at those node regions. Only at those maximum antinodes are you going to actually generate sound with the guitar strings. All right. Now, standing waves all have certain characteristics that you need to be familiar with. The antinodes generate those high and low points, which we call either a wave crest or a peak. Sometimes the wave crest is called a peak, or a low point, which is called the trough or the wave trough. All right. Now, we also introduce a vocabulary word known as the wavelength. The wavelength for a standing wave is defined as the distance between two consecutive peaks or troughs in a standing wave. The units that are usually found in standing waves are going to be in meters or nanometers, depending on the distance from wave crest to wave crest. So for instance, if we go back to our diagram again, we can see that from this crest to this wave crest, this distance here is known as the wavelength. The symbol for wavelength is used a Greek letter called lambda, and it looks like a weird wishbone or upside down Y, and that is lambda. All right. Another characteristic of standing waves is frequency. Frequency is simply the number of waves or cycles that pass a given point in every second. All right. So, for instance, say I have a point in space here. And what we're going to do is we're going to count the number of waves that pass that given point in 1 second. And that will give us the frequency. So, for instance, usually we would count the number of wave crests that would pass this point in every second. The units for that are either going to be in hertz or in cycles per second. So, for instance, let's say, let me erase this. Let's go to our diagram here. And let's say we have a point in space. Point in space right here. And what we're going to do is we're going to begin to count the number of wave crests that pass that given point. And we're going to do so until 1 second has occurred. So let's say that after we've counted 1 second, that there's 1,000 of crests that pass this point in 1 second. And so therefore we call that 1,000 hertz, or 1,000 cycles per second. Okay? And it's just simply the number of crests that pass that given point in a second. Right? Hopefully that makes sense. Frequency is sometimes hard for students to understand for the first time. We also have amplitude. The amplitude is defined as the vertical distance from the midline of the wave to the peak or trough, and it's usually related to the wave intensity. The higher the amplitude, the brighter the wave is going to be, or the more intense it's going to be. So again, looking at our diagram in your notes, the amplitude, here's the midpoint, and the amplitude is the height from the midpoint to the top of the wave crest. All right, and again, here's the wavelength, the distance from crest to crest, and then the frequency is the number of wave crests that pass a given point in 1 second. And so those are the common standard characteristics or definitions that you should know for standing waves. So this is all for this particular lesson. Make sure that you study it really well. Know what wavelength is, know what amplitude is, know what frequency is, and basically just know generally how a standing wave is generated from two fixed points. And that is it for now.